Welcome back, ladies and gentlemen. As promised, let's look at the analysis of the R-to-2R. We saw how even when we were talking about the pros and cons, merits, demerits, they may call them advantages, disadvantages. You saw how we said it was easy to deal with the weighted resistor. But then now, when you're looking at the R-to-2R, hey, it's a little bit of a nightmare. But let's go through the nightmare because what doesn't kill us can only make us stronger. Welcome back and hit that like. If you like, you're not going to like today, but you're going to like not liking. So like it anyway. So now what you're going to do is we're going to analyze. We've seen this circuit before. It's not the first time. So let's look at what it is. We've sort of lost track. This is supposed to be R-to-2R. So all you see there, wrong color pen. We need that to be the R-to-2R. So everything else is either R or 2R, R-to-R, 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 R-to-R. So this is the R-to-2R. Now it is, how do we analyze this? I'm going to say, obvious common sense says this is going to feed the op-amp. So obviously, if you look, these are switches, therefore we either feed zeros. So we are going to range from zeros when we have our switches on ground, and then we are gonna be able to feed the one. No, wait. Now let's look at this. Where is the one? Common sense says, remember that the one that contributes the most voltage is more significant. So obviously there's less resistance for this guy than there is for that guy who has to go through all those resistors there. So it is obvious therefore in this circuit that this is the MSD here. This power source is going to contribute a bigger chunk into the op-amp than the lower order ones, because there's more resistors, therefore less current is bound to go through, and therefore this is the LSD here. So I would say, since we only availed since we only availed 4, this is gonna be A, B, C, and D. So our switches, therefore this is switch. So our switches can either all be off, and then we can have a 1. The count 1 would be that switch going on. Okay, the count 2 will be this switch going off, but the other one going on. This is what? This is the count 0010, which is our 2. All right. So, and so on and so forth. So this is basically our switches can run all the way up to from 000. What I'll do is I will say 000 on the ground, 2 all the way to all of them closing. I'll choose the red for close. 1, 1, 1, 1 and 1. So our 1 being that, and that, because our MSD is that side. So remember, it's A, B, C, and D from 0000 all the way up to 1111. All right. So what we want, therefore, it means that our step is the D. So we want to try and calculate our step voltage here. We are going to calculate the D. How do we do this? It means, remember, this circuit here, all right, there is 4 supplies here. This is a little complex scenario. So what we need to do to analyze this, it is best if you go back to our basics. You remember that with the Kirchhoff, we started off with the Ohm's law, the Kirchhoff. Remember the Ohm's law, the voltage dividers, the current dividers. Then when we came on to Kirchhoff, we then learned Thevenin's theorems, we learned superposition, all those methods there. We'll apply whatever needs to be applied to get what we need, what is best to apply at any given time. So now we want to see It is difficult to see what they would all do at once. It is therefore easier to analyze them one by one. What I'll do is this. I will say, let's start with the LSD and say, let's do the LSD rather, and say only the switch is closed there. The rest are open. The rest are open. So what does it mean? It means we have to analyze. What we're doing here is, if you analyze the LSD, whatever the LSD contributes there, let's say this is the point A, the point of supply, the output that will be fed into the op-amp. Let me rather detach the op-amp a little, okay, and say this will be fed into the op-amp. All right, this is the output. So we want to know what the D will supply at point A, what I will call V A from D. All right, why? We would want to know what this contributes will be called here. It will be called VA, but from source D. All right, what this C will contribute to be called VC from source. Oh, what am I saying? VA. What it contributes at A, but from source C. I think you see this presentation with what? With the superposition method. So we want to know what VB, the B source contributes at point A, which we call VA with B source, and then this one will be VA from that switch, from that supply there. So now, let's go ahead and calculate this VA from source D. So what happens at the end? They together will superimpose. Therefore, if you calculate them individually, at the end of the day, what's going to happen is that they are going to be added together. Why? Because the positive voltages of, we are going to say, assuming conventional current, the currents are going to go that way. You can see they're heading in the same direction. Therefore, at point A there, they will have what? They will have summed up together. So, but this is the Thevenin voltage. At the end of the day, what you will have is the voltages will work out. The individual voltages will sum up them with the so we'll do the superposition method, treat them individually, sum them up, and then we will call that sum V Thevenin. So, but as we know, V Thevenin goes with R Thevenin. So at a later stage, we're going to look at R Thevenin. But let's start with V Thevenin. But that V Thevenin starts with what? Superposition, with us dealing with each individual source and seeing what is going to contribute at point A. Let's start. So V A from source D will thus be, let me take this a little bit up. I know that I will have a problem with space. So let me rather assume I will have a problem. Let me rather be preemptive here. So now what we're going to do is we're going to say, with this source closed, everything else is therefore on ground, because remember, with superposition we only allow one source at a time, so everything else is grounded. All right, so what then happens is, let's analyze the circuit with everything else grounded. I will remove these arrows here because they are going to create problems for me. I was just explaining, but visually they create what I'll call a crowd. Right, so this one is the only one at 1. So what does it mean here? It means that if you look at this circuit is a supply. That part, maybe let me redraw that part and take it up and say this is the 5 source, just to make it clearer for some people. I almost did it, but I thought let me just clear it out because some people may not see what we are referring to. This is our supply through the 2R resistor to that point there. Right, let's call that point there X. Right, so this is point X. Okay, then point X is connected to that 2R, which goes to ground. which goes to ground. Now, the rest of the circuit as it is, I could actually go and copy this circuit as it is. The rest of the circuit as is, the rest of this circuit here is actually, I can copy it and bring it here. Oh, okay, I'll take it up because I obviously don't have, I'll put it here. So now what I want to indicate here is that I don't want to have a conflict. So what we'll do is ungroup. Okay, I want to remove these two resistors, this resistor here from the 5 source. That resistor there is that one there. So what I'll do is I'll remove that. I don't have a rubber, so that there I'll remove. Oh, I want a rubber, so I remove that. All right, and then that resistor there is that resistor, so I'll remove that as well. What do I have left? I have point X is that one there, so I can bring point X to point X. I think that makes our, it's not grouped. Let's rather group it first. I brought point X to point X. This is the same point, so I brought it to point X. So now what has happened here is, what happened to our MSD? Our MSD is the one, our LSD, it is the one that is connected to the source. Remember, LSD was connected to the 5 volts. So this is our LSD. So we want to work out the contribution from that LSD. So let's go and say, let's calculate now. Where do we start? In a scenario like this, I'll start from the outside. So I'll start here and call this R series 1. R series 1 is this guy in series with the 2R resistor in series with the R. So now what then happens is that we've got R series 1. And R series 1 is simply equal to the 2R in series with R, which is simply 3R. Easy enough. What I'll do is I'll come back. You remember that we're doing this. We're going to do R Thevenin later. We're going to do, you're doing both the Thevenin, we're going to do R Thevenin. So, R series 1, what I want to do is I want to list it somewhere. No. Let me leave it there. Let's go on and do. The next part is 2. So, this is now like 1 voltage. So now it's going to be in parallel with that. Why? We have a scenario. I'll just redraw this part. I'll just redraw this part. This part now is now 1 resistor. It's now 1 resistor, which we've called 3R. And it's connected to ground. Because they were connected to, both of them were connected to ground. Now they come there and they connect to the 2R. These 2R. Therefore, and this goes to ground. So, if that's the case, what does it mean? You can see that ground is ground, so this is as good as connected together. So these two, this is going on. This is going on here. This is the part that I'm drawing here. Okay, so what has happened is that these two have become 1 resistor, which is 3R, and then parallel with that, which is that thing. So we need to work out R what I will call R parallel 1. So R parallel 1 is simply equal to 2R parallel to 3R, which is equal to, remember parallel resistors. How do we add parallel resistors? We say R parallel for 2 resistors, let's call them R1 and R2, is going to be R1 times R2 over R1 plus R2. So if we go to this to be R1 and R2, this will be 2R times top part is going to be the product 3R over the sum 2R plus 3R. So on top you can see is 6R squared over 2R plus 3R is like 5 cows plus 2 cows plus 3 cows, which is 5 cows. So that's 2R plus 3R is 5R. R into R squared will leave us with 6R over 5. So that there is our, let's remove this. This was just to explain what we are doing here. So what we are doing basically is we are not this, we are now doing, this is the parallel network. Oh, no. I need a pen rather. This is the parallel network that we are talking about. This is the R parallel 1 network. These two were in series, which was those two, but then they are parallel with that one there. What we need to do next is we need to put this resistor, and this is obviously these ones here become one resistor. If I just take R, I will say R. What happened to this network? It became one resistor which we call R parallel 1. So it became R parallel 1. So this is this R, okay? This R in series with that network that we just called R parallel 1, R parallel 1. So what do we have to do here? We have to add this now. So we go ahead and add. So what are we going to call it? We are going to probably use a different color. Let me say, now we are going to call it R series also because it's a series resistor. So we are going to say R series. We can't call it just because this is R series 1. We need to call it R series 2, which means adding that R to that parallel network. So that will be R plus that parallel network, which is 6R over 5. And that is what? This is the same as R over 1. So if we make it both over 5, it's going to be 5R. 5R plus 6R is 11R. They are both over 5, so it's now 5. All I did was, once I changed that to 5, this must be 5 times bigger. If the denominator becomes 5 times bigger, the numerator must go 5 times bigger as well. So this will be 5R plus 6R, which is 11R over 5. So that is that. I don't think there's anything difficult so far. What we're going to do, we've taken care of up to this point. We have resolved up to that point there. Alright, now what I'll do is, let me remove this because it's cluttering. It's cluttering. Let's remove the clutter. So we have revolved. R series 1 was this 2, R parallel 1 was this one, then R series 2 is this one. So now we're going to do R parallel with that one there. So what we're going to do now, we're going to go and say, let's do R parallel. I like to keep changing pens, but I'm running out of colors. Let's try this one here. Let's go and say we are going to do, we've done R series that, this was the one. We've done R parallel this and that was the R parallel. We've done the R series 2, which was that and that. Now we need to do same with this R parallel 2, this R series 2 rather. R series 2 is now one value. This whole part is now called R series 2, but it's parallel to that 2R. So because they are connected there, once I replace this with R series 2, they are both going to ground. So ground is a common place. So this is what we're looking at here. This is our ground. So these are now parallel. So what we go and do, we go and say, what do we call that parallel? We call it R parallel 2 because R parallel 1 is taken. So we say R parallel 2 will be equal to, is this 2R? Parallel to R series 2, therefore R series 2 is 11R. So remember, parallel we say times 11R over 5, but we say divide by, the sum. So it's 2R plus 11R over 5. Now, what does this give us? It gives us, this is a simple product. 2 times that is going to be 22. R times R is R squared all over 5. divide by that fraction there. If I say this over 1, if I change this to 5, I must multiply that by 5. That's 10R plus 11R, that's 21R. 21R over 5. Because we've changed both to 5, so we can add them now. So 5 resolves 5. R resolves the one of those, and then we've got our value as 22R over 21. That is R parallel 2. What have we done? We've done all the way up to that, because R series 1, R parallel 1, R series 2, R parallel 2, which we just did now. Now we need to add this guy. This is simply in series. With that, I don't have to do this anymore, because I've done up. This is our R, and we just did this parallel network, now R parallel 2. Okay, so it's now in series. So what do we do now? We add it up. Let me not clutter again. You need to understand basics. I mean, sometimes when you don't have basics, really life becomes a problem. So now we need to add that guy up. We're gonna say call this R series 3, because 2 is taken. R series 3. I will use a different color. Probably let me go back to red just to have contrast, so people can. Let's say R series 3 now. It's going to be that resistor R added to the whole parallel network we've just been dealing with. That will be 22R over 21. Now to add this shouldn't be difficult. What do we do? We say rather say R over 1, so that we can change this to 21 by making that 21 times. This 21R plus that 21 plus 22 is going to be 43R. Now there's a common denominator because we change this to 21, so this is what it's going to be. So that was straightforward. But before we get there, we have to get a final parallel value, because this whole value will become one value. All this will become that one value, R series 3. So it is in parallel. That will be in parallel with the 2R. So we have to get R parallel 3. So they have to change colors just to. I don't know what color I should use, because I don't want. I don't think this is nicely visible. So let me rather take the one again, but I'm not happy. So let's go and say now for the final part R parallel 3, not final part, but for that part R parallel 3 will be equal to that 2R parallel to this value, that whole parallel value there that we just I don't know what that is. I don't know. I just what did I call it? I can't say I encircled it. Well, I tried to encircle it, but that's what they said. Probably ovaled it. I don't know. It's more oval than circular. So anyway, let's go and say it is that part there. So it's parallel. So it's gonna be times. We go back to this. It's gonna be times then plus. So this is 2R times 43R over 21. This divide by the plus part, which is 2R by plus 43R. Oh, 43, not 4R. 43R over 21. Okay, so this here I would like to slide a little bit to give myself space. This here is the same as this here is going to be a direct, so that's 86 R squared over 21 divide by this here. I can make that over 1, then this is 21. I must make that 21 times bigger. That will be 42R. 42 plus that is 85. 85R over 21. Now it's 21 21. Okay, what we have is R into R, so we've got 86R over 85. Okay, so what do we have here? We have got that part is R series 3 R parallel, so we've got that part. Our final part is the total part. So R total now, R total, I'll do a different color for contrast more than anything. So our R total is going to be, let me go and say, let me do my R total. Let me remove this. You'll remember that that's how we do parallel resistors. So R total is equal to, you add that to the parallel network. This is now a parallel network. From there, is parallel, that value is parallel to that. We just did it here, parallel 3. So this is in series, so we do 2R. Series means add plus that R parallel 3, which is 86R over 85. Now, adding this means this has to be twice that. This is 160, 170, that's 170 R plus 86R over 85. Okay, if I put that, the common denominator will be 85, so that there will be 85 times 2, that's 170R. So this is going to be 15256 R over 85. So these are our values. Now this was to help us analyze. Do I need it now? No. Okay, now I can go and list my values just because I think I'm gonna need that space to recalculate. So what I will do now is I'll go and say, what was my RS1? It was a simple sum, which was 3R. If you can't remember, you can go revisit how this was all done. What was my RP1? It was 6R ultimately over 5. I'm just consolidating my results here. Then my R series 2, as I went through it, R series 1, R parallel, R series 2 was R series 2 was 11R over 5. That's that. Now that was R series 2. R parallel 2 was R parallel 2 is 22R over 21. Then R parallel 2 was that. We've got another R series, which is R series 3. R series 3, R series 3 starts from there and the rest. R series 3 was simply equal to 43R over 21. And then we had that parallel network from X all the way there. That was our R parallel 3, which was equal to R parallel 3 is 86R over 85. And then you'll be like, but why aren't you giving values? I'm not giving values. These things are going to resolve themselves. I can do it, but it won't really cause, it will just take much longer to achieve no real difference. So the final one is when we added our resistor here. Okay, our resistor here was R total, which is equal to 256 R over 85. Okay, now we go and say I wanted to just get these things out of the way because I need to do more calculations in this same space. My board is finished. I have to go and All right, try again. Now, what we're going to do is this: using this result, we're going to start calculating values now. Our first value is going to be, we want to know the voltage. This is 5 volts. We want to know the voltage there, which is the parallel network voltage. So it is going to depend on R parallel 3. So V parallel, or V at the point X, I'll call it V parallel 1, because it is from the voltage across these two R resistor and the voltage across the other network. So V parallel 1 is going to be the R parallel over the R total, R parallel 3 over the R total, R parallel 3, which is R parallel 3 over R total times the supply, which is equal to 86 R over 85 times, not divide by, R total 256 R over 85 times V of 5, the voltage. When you close the switch, it's going to supply us with 5 volts. Those two resolve, the R's resolve. Now what do we have? We've got the 2 goes there 43 times, 2 goes there 128 times. So this is going to be 128. Now 43 times 5 is going to be 15, then 20, 21. 21 over 128. Okay, so this is our, I'm multiplying that by that over 128. So what is, then once we've got that voltage, we need the voltage here. The voltage here is based on R parallel 2 and R series 3. So V parallel 2, because it's a parallel point, this is a parallel point also. So this is a parallel point. So this, we'll call this V parallel 2, because we call the voltage at X V parallel 1. So V parallel 2 is going to be equal to this parallel network, which we will call R parallel 2, okay, over, that is the last series part is R series 3 times the voltage V parallel 1, because they are sharing that parallel voltage there. The rest of the resistors are going to share that resistance. So that parallel part over the total, the total is that R series 3. All right. So for the total for that point, so that will therefore be equal to R parallel 3. R parallel 2 is 22 R over 21 divide by R series 3, which is 86 R over 85 times the voltage there, which is 215 over 128. Now that there, no, this is supposed to be R series 3. I've used the wrong one. This is supposed to be R series 3, 43 R over 21. 21 R into R. Now we've got, let me see this resource, because this is going to be 11. 2 there is going to be 11. 2 there is 64, which is going to be equal to, let me rather put it here. Okay, which is going to be equal to, now 11 times 215 times 215 11 times 2, 15. Divide by 43 times 64. Is 55 over 64. So this is 55 over 64. So we keep that there. Now, we want to know, we've got the voltage here, V parallel 2. What we want now is the voltage here, which is V parallel 1. 1 V parallel 1 here. V parallel 1. So what we go and do is say V parallel 1. What is V parallel 1? It is R parallel 1 over R series 2 times the voltage V parallel 2, because they are sharing that voltage. This resistor and that network are sharing that voltage. So what is it going to be? R parallel 1 is 6R over 5. And then R parallel 1, R series 2 is 11R over 5. Divide by 11R over 5. These times the voltage that we just calculated now, which is 55 over 64. Now 5s are going to resolve R and R. What do we have now? We have 2 there giving us 3. Okay, 2 there giving us 32. 11 there giving us 1. 11 there giving us 5. That is going to be 15 over 32. Okay, that is V parallel 1. Now, V parallel 1 is going to be the final part that we are going to do now, is going to share V parallel 1, because V parallel 1 is across these two. So we're going to share one. Now we're going to get the voltage at what? At A. V, therefore, VA, it was supplied by the D, because remember the other sources that can supply there, so we must differentiate, is simply going to be that 2R over the total 3R times they are sharing V parallel 1, which is simply equal to 2 over 3, because the R's are going to cancel. 2 over 3 times 15 over 32. Now this is going to be 3 there is 1, 3 there is 5. Then 2 there is 1, 2 there is 16. So our answer is 5 divided by 16. 5 divided by 16. And our answer is 0.3125. This is exactly our step voltage. What does it mean? It means 0 volts will be 0. Yes, when all switches are on 0, 0 volts going to be 0. 1 volt, or sorry, 0001 is going to be this value, 0.315, because this is D corresponds to the unit. Now, it means therefore 2 is 0010, which is the next step. It's going to be 2 times this, which is 0.625. If you remember, I gave this as homework. I have tried to do it as slow as I can in this part, because the other part I thought were a little bit too fast, but I don't know whether this was still a little bit too fast, because if your basics are not sound, things are a little bit too tough. Probably you should go back and look at the videos where the basics are dealt with, where the voltage dividers are dealt with, where the current dividers are dealt with, where the simple basics are actually tackled. Then probably this won't look as much of a nightmare as it is. So we know that this here contributes, if all switches are closed, the LSD, the D part, will only contribute that voltage. All right, so this is also our step voltage, because it is there, the 0001. So every step, remember, will increment by 1 in the digital thing. It will increment by 1, so it means it will keep incrementing by that step voltage, the increment. Now I hope this was fun. It was a little bit long. Remember, I said this analysis is a nightmare, so I hope you do not have you do not see Count Dracula today. You don't see Count Dracula in your dreams today because of the operational amplifiers R-to-2R simple analysis. I hope you liked it. I promised you're not gonna like it, but I did say you're gonna like not liking it. So like us anyway, because we are trying our best to show us the appreciation and the love. And please do subscribe, because we won't, I don't know how else you can know that we've got new work for you that might be very useful for your studies. Keep studying. Let's take them down one by one. Till we meet next. Ciao.